In this tutorial screencast for radical chemistry, we're going to look at the thermodynamics of radical reactions. To understand that, we first want to be able to interpret homolytic bond dissociation energies. And so in problem number 1 here, we're asked to find the change in enthalpy values for cleavage of a CH bond. So this is strictly looking at a table and then writing down the values, and we're going to use kilojoules per mole throughout this discussion. So methane, we're looking at CH4, and the value in our table for that is 440. Again, these are all going to be in kilojoules per mole. Ethane, we have CH3, CH3. So there's only one type of CH bond in ethane, and so that drops quite a bit to 421 kilojoules per mole. So propane, we're asked to find what the CH homolysis of a primary hydrogen. So there's propane, and if we draw in one of the primary hydrogens, it would look like that. And this is 423 kilojoules per mole. Propane again, we're going to look at the secondary hydrogen. And now this one drops about 10 kilojoules per mole, difference from the primary to 413. So what about 2-methyl propane? And it's asking to look at the tertiary hydrogen. So here's propane, there's 2-methyl propane, and the tertiary hydrogen would be that one. And this is 400 kilojoules per mole. Propene, this is the 3-carbon alkene, and it's asking us for the primary, which is that hydrogen, and so this is 369 kilojoules per mole. So that's significantly lower than the tertiary CH bond in 2-methyl propane. Methylbenzene, otherwise known as toluene. Again, that primary sp2, sp3 hybridized carbon H bond, this one's worth 375 kilojoules per mole. So again, these were values just taken from a table in the textbook. In problem 2, we're asked to draw the structures of the radicals that each molecule from part 1 forms, and paying particular attention if there's any resonance contributors for some of these. So if we're looking at CH4 forming a radical, this would form the CH3 methyl radical. So ethane would form the ethyl radical. So keep in mind, I'm drawing these a little bit different each time just to show you how radicals can be represented. So if we have propane, and we want to show the primary radical. So again, the carbon is bearing the radical, and that radical resides in an sp hybridized orbital, sp2, excuse me. So we'll draw propane this way. We're looking at the secondary in this one, so that's the secondary radical. We have 2-methyl propane, and we want to show formation of a tertiary radical. It would be that. So the tertiary hydrogen forms the tertiary radical. So here's propene. We're cleaving the sp3 CH bond. We form this radical, which is a primary radical, but it also has a resonance contributor. So I'm using the double-headed arrow to show that. And so we can show the fishhook notation to show the resonance. So the allylic radical is another name for this, allylic system. Has resonance forms, which is one reason why the bond dissociation energy is so much lower for this primary hydrogen than the other systems. And finally, we're going to do the methylbenzene, which is toluene. Again, when this cleaves, what is formed is a primary radical. In this case, it's called benzylic. And this has resonance stabilization as well. What you can notice, and I'll draw in blue pen here, we have the radical at the 1 carbon, then you have a pi bond next door, 2 and 3. So this resonance form is basically moving the radical from the 1 position to the 3 position using that fishhook arrow pushing. So this will also have 2 more resonance forms where you can move that radical again from this 1 position to the 3 position. And then there'll be another resonance contributor where you're moving it from 1 to 2 to 3. So the more times you can draw a resonance hybrid, that really indicates stability. And so this gets into the third question, which is asking us to rank the molecules in order of ease of hydrogen abstraction. The easiest on the left here corresponds to the smallest numerical value for the CH homolysis, and that's going to be the propene. So let's go ahead and draw these structures out in terms of an order. So again, we had this was plus 369 to cleave that bond homolytically. So this is the allylic hydrogen. For the methyltoluene, this was the benzylic hydrogen. This was plus 375. So the tertiary hydrogen in 2-methylpropane was next at plus 400. So tertiary. Then we had the secondary hydrogen of propane, which was plus 413. Then we had the primary hydrogen of ethane, which was 421. Then the primary hydrogen of propane, which was 423. And then the CH bond of methane, which was 440. So really what we're looking at is a trend from easiest to hardest of cleaving the CH bond homolytically. And so what you want to pay attention to is allylic and benzylic are special in that they're primary, but they have resonance stabilization. Next we get into tertiary is more stable than secondary, which is then more stable than the primary. So this order is a trend of homolysis of CH bonds of different functionalities. And in the next problem we're going to examine homolysis of CH bonds where the carbon is not sp3 hybridized. So that's going to be question number 4. So it says find the delta H values for CH homolysis of the indicated bonds. So what I want to point out now is it's important to recognize the hybridization of the carbon bearing the hydrogen. So here we have ethylene. This carbon is sp2 hybridized. So we're looking at a C-sp2H bond, which is different from the prior cases that were all C-sp3H bonds. So if we look in our table, we'll see that this is 465 kilojoules per mole to cleave that homolytically. Again, we have an sp2 hybridized carbon. This is plus 474. Now this carbon is sp hybridized in acetylene. So we go up quite a bit, where we have 574 kilojoules per mole now. So you're able to now differentiate these homolytic dissociation energies based on hybridization of the carbon. So a sub-question here is asking us, why are these values significantly greater than those of part 1? So we have to understand a little about where that unpaired electron is ending up in the homolysis. So in the problem molecules in problem 4, the radical itself is ending up in either an sp2 or sp hybrid orbital. So that's different from the original cases because the radical in those are ending up in a p orbital. So say, for example, we have, we'll do this allylic case, where you have an sp3 hybridized carbon, and we're homolytically cleaving that CH bond. So keep in mind you're left over with 2 hydrogens on that carbon, plus you have your hydrogen radical. So other than a dot being associated with that carbon, what type of orbital is that radical residing in? It is residing in a p orbital. So let's draw that out so we can understand. So we'll draw that over here. So you know that an sp2 hybridized carbon has 3 substituents and an empty p orbital. And that's what that radical resides in. So you're starting off at sp3. When you cleave the CH bond, the carbon ends up as sp2, and the radical is located in a p orbital. That is very important to understand, because in these cases up here, when you cleave the bond, the radical ends up in either an sp2 orbital or an sp orbital. And that's why these values are significantly higher than when you're just starting off with an sp3 hybridized carbon. In question 5, we're asked to determine the enthalpy change for the reaction using the equation delta H is equal to delta H of the reactants plus delta H of the products. So again, we're going to use the reaction of methane plus chlorine going to methyl chloride plus hydrogen chloride. So on the reactant side, bonds are broken, and so that requires energy to be put into the system. On the product side, bonds are made, so energy is released. And so I've drawn out for each of these chemicals which bonds are being broken or formed. So that ends up being, if we look, we have 1, 2, 3, 4 half reactions we have to find values for from our dissociation table. So here's 1, 2, 3, 4. So in the first one, we're cleaving a CH bond of methane. So there's our fish hooks. We're forming the methyl radical and the hydrogen radical. And the energy to do this is 440 kilojoules per mole. The second reaction here, we're cleaving molecular chlorine to get chlorine radical, and that requires 243 kilojoules per mole. So we get plus 673 kilojoules per mole have to be put into the reaction to break those bonds. So for the products, we are forming bonds, and so energy is released. So this radical combines with that radical to get methyl chloride. And then this is going to release 352 kilojoules per mole. We have hydrogen radical combining with chlorine radical to give us hydrogen chloride. That releases 432 kilojoules per mole. We add that up, we get negative 784 kilojoules per mole. And so the delta H for the reaction is the sum of those two. So I'm going to write it this way, plus the negative 784 kilojoules per mole. When we do that, we end up with minus 111 kilojoules per mole. So this reaction, as it's written, is exothermic, meaning that heat is released into the environment. In this problem, we're going to look at the first three steps of a free radical chain reaction mechanisms with the different molecular halogens and consider the homolytic dissociation energies for each halogen, and then try to understand why the reaction really only will work with chlorine and bromine. So the first step here is the initiation step. And so this consists of the homolytic cleavage of a molecular halogen into two halogen radicals. And so what we're simply doing over in these columns here is writing down the homolytic dissociation energies in kilojoules per mole. So simply from a table, we have 159 for fluorine, 243 for chlorine, 193 for bromine, and 151 for iodine. So keep in mind that we are breaking a bond, so we have to supply energy. So step 2 is the first propagation step. And so the halogen radical that we produced from step 1 is now coming down to step 2 to abstract a hydrogen atom from methane. And so how does that work? So we use the fish hook arrow notation. So this radical will abstract a hydrogen. We're going to cleave that bond, so we need one electron from that bond to form the new bond, and then the other electron goes onto the carbon atom. And so we're ending up with methyl radical plus HX. And so to calculate the values for these columns now, we're looking at the cleavage of a CH bond in methane, and so that was worth plus 440. And then we have to look up these different HX bonds. So from our, since these are bonds that are forming, we are going to assign them as negative. values because they are releasing energy. So let's go ahead and make a little table. Fluorine, chlorine, bromine, iodine. HF releases negative 570 kilojoules per mole. So if we take 440 and subtract 570, we're going to write minus 130 kilojoules per mole in the fluorine column. Chlorine is negative 432. 440 minus 432, we get plus 8 kilojoules per mole in the chlorine. The bromine is negative 366. So we take 440 minus 366, we get plus 74 kilojoules per mole. And then finally, iodine is negative 298. And so here we're going to get plus 142. So what we want to understand what these numbers are telling us for this propagation step. So in this step, when we add these, the energy required and the energy released to get these energies in this column, negative 130 plus 8 plus 74 plus 142, that is the energy that's either released or required for this step to proceed. So now we're going to move down to propagation step number 2, which is the third step in the free radical chain reaction. So now we've already seen what these values here are from step 1, the initiation step, and we've written them in these columns here: plus 159, plus 243, plus 193, plus 151. Now when we go to our table, we're going to look up these values for the formation of a carbon halogen bond. So fluorine, chlorine, bromine, iodine. So on our table, we're going to find that a methane fluorine is going to release negative 461. So what we're going to take to get this number is plus 159 minus 461 gives us negative 302 kilojoules per mole. Chlorine, we have negative 352 plus 243, that gets us negative 109. Bromine, we have negative 293 plus 193, that gets us minus 100 kilojoules per mole. And finally for iodine, we have negative 240 plus 151, we get negative 89. So now let's understand what these numbers are telling us. Then in propagation step 2, which is producing this radical, halogen radical, I'm going to underline in blue, because this is our product here. This is what we're looking to form. And so at this point, let's consider that inert. So this halogen radical, which I've labeled X dot, and this will answer the next sub-question here. This is the propagating radical. So what these numbers are telling us, that is the energy produced for that step of the free radical chain reaction. And basically what we're trying to compare is that energy produced enough energy to sustain the prior step. And so we're going to, in the next sub-question of this, compare those energies and see if the reaction can sustain itself and be a true chain reaction. So what we're going to do on this next thing is just write down the values. So from step 2 we have negative 130 for fluorine, plus 8, plus 74, plus 142. Those were step 2 values. Step 3 values, we have negative 302, negative 109, negative 100, and negative 89. So what we are looking for is energy to be released from the second propagation step that will overcome the energy needed for the first propagation step. If we take step 3 divided by step 2, we see that for fluorine we get 2.3, chlorine we get 13.6, bromine 1.4, and iodine 0.6. So if we analyze the situation for fluorine, both of these values are negative, and that's not necessarily the best thing when heat is evolved and we're talking about selectively substituting a CH bond in any particular molecule. What this tells us, since both values are negative, fluorine is not selective. We're generating too much heat in the second propagation step to really selectively go after a primary versus secondary versus tertiary hydrogen in any particular molecule. If we look at chlorine, we see the ratio is about 14. And so what that's telling us is we're producing an ample amount of heat in the second propagation step to overcome the plus 8 kilojoules per mole in the first propagation step. But the amount needed is 14 times what we need, and so that's telling us that chlorine, it will sustain the free radical reaction, but it will not be selective in primary versus secondary versus tertiary. Another way to think about that, once you classify all the CH bonds in a molecule, you can be reasonably certain that you're going to get a large product distribution of primary versus secondary versus tertiary substitution products. Bromine, we can see the number drops to negative 100 kilojoules per mole as evolved in the second propagation step. We only need to overcome plus 74 kilojoules per mole in the first propagation step. So that ratio is 1.4. So bromine is going to be more selective. In which CH bond the bromine radical abstracts. So bromine is more selective in which CH bond is cleaved to form a carbon radical that then gets carries through to the second propagation step. Finally, you can see for iodine, the ratio is 0.6, but we're only producing negative 89 kilojoules per mole, and we require 142. So the second propagation step does not supply enough energy to propagate the first radical chain reaction, step 1. So this reaction will not be a true chain reaction. Essentially, it'll go through once and just stop. So this is what we can take away from this is that we have this reactivity of chlorine versus selectivity of bromine. So if we're looking to be selective in substituting a CH bond, we would want to do radical bromination, because the bromine is going to basically go after the weakest CH bond in a molecule. Chlorine, on the other hand, sees all of these CH bonds and has enough energy to break pretty much any of them. So you get a wider distribution of products. So in this last part, we're going to look at the relative reactivity of the chlorine versus bromine data. And we're going to do it for this reaction in which we have our halogen radical, and then we have this very broad CH, where that can be primary, secondary, or tertiary CH bond to form the chlorine or carbon radical plus HX. So we're going to examine both chlorination and bromination because, like I said, we already determined that they will sustain the free radical chain reaction. And now we're going to look at the values for abstracting specific primary versus secondary versus tertiary CH bonds for each. So we go to our table and we find a primary CH bond, such as that found in ethane, plus 421. So these values will be the same in this column for both chlorination and bromination. A secondary CH bond will be 413. So this is the value for the CH bond in propane. Tertiary, now we're looking at the 2-methylpropane value, and this was plus 400. And then this number here, HCl, for this entire column, this is going to be negative 432. So that value is staying the same. Now we're adding these together. We get negative 11, negative 19, negative 32. So let's put this into context of what this is telling us. When a chlorine radical and your substrate, which has a CH bond, depending on if that CH bond is primary versus secondary versus tertiary, the abstraction of that hydrogen, if we do the fishhook arrow, to give you carbon radical plus HCl. A primary hydrogen evolves negative 11 kilojoules per mole, a secondary negative 19 kilojoules per mole, and a tertiary hydrogen negative 32 kilojoules per mole. So they're all evolving energy, and that's important when we compare that to the HBr case here. Again, this is going to be negative 366 for this entire column. We're going to add these together. We get 55, 47, 34. What we want to pay attention to in this column, these values are all positive. So this is energy that has to be put into the system to break those bonds. So when the halogen radical, the bromine halogen radical, and the substrate react, that radical is going to go after a tertiary hydrogen because it's the easiest bond to break. It only requires plus 34 kilojoules per mole. A secondary requires 13 kilojoules per mole more than that at 47. And then a primary CH bond requires a total of 55 kilojoules per mole. So the bromine radical wants to expend as least energy as it can abstracting that hydrogen. So in the next part of this exercise, we're going to look at this in relation to a time and energy plot, considering this molecule 2-methylbutane. Let's go ahead and determine the unique number of hydrogen sets we have, and then classify each of those. So let's put the numbering in. So this is carbon 1, 2, 3, 4. So that's our butane chain. Then at the 2 position we have a methyl group, and so we see that at carbon 2 there's a methyl. So if we analyze this, it appears that we have 4 unique sets of hydrogens. So we have some methyl groups, CH3 groups. There's 3 CH3 groups. 2 of those methyl groups are equivalent, so that reduces our number of sets. So far we have 2 sets, then at the position 2 we have a tertiary hydrogen, position 3 we have 2 hydrogens. So overall we're going to have 4 unique sets. The ratio of those sets will be 6 to 3 to 2 to 1. So I've written them in that order so that we can classify them as 6 primary, 3 primary, 2 secondary, and 1 tertiary. Let's go ahead and, so we're all on the same page, write that in. Next to them, so I'll do it in blue so the numbering is different. So these are primary, these are primary. Carbon 2 has the tertiary, carbon 3 has the secondary, and carbon 4 has the primary hydrogens. And so we need to be able to do that so that we can go back to these values that we just calculated and understand which hydrogen is preferentially abstracted. So again, the sign of the delta H is telling us which hydrogen is preferentially abstracted. So in this last part, it says, how does the delta H for primary versus secondary and tertiary in both chlorine and bromine help explain the relative reactivity values calculated? So chlorine was 3.7 times and bromine was 97 times secondary versus primary. So the energy coordinate diagrams are shown, and we're going to put in the values that we calculated from above. So we have our molecule 2-methyl-1-butane. So we're looking at these different primary versus secondary versus tertiary. So we know that because the sign of the delta H value is negative, that these energies here must be below our starting energy of our molecule. So for a primary, we're evolving negative 11 kilojoules per mole. A secondary, negative 19, and a tertiary, negative 32. So because these values are negative, the chlorine radical will really abstract any of those types of hydrogen. For bromine, we saw that a primary hydrogen required plus 55. So now the difference is from our starting energy of 2-methylbutane, these values are positive. So we're going up. We have to put energy into the system to break these bonds. Secondary, we have plus 47, tertiary plus 34. So if you imagine that you are walking on this curve, it is much easier to get to a tertiary energy than it is to the secondary or the primary energies. So this is what we call selectivity. The bromine's going to put in energy to go to the most stable radical, in this case the tertiary, versus the chlorine, which we call reactivity. Because all of these values are negative, it can abstract any of them and give you multiple products. So overall in this worksheet, we've used the homolytic dissociation energy table to understand the thermochemical component that is required in a free radical chain analysis. And what we've learned is that of the halogen series, chlorine and bromine are the two halogens that will sustain a free radical chain reaction, whereas fluorine and iodine will not, for various reasons. We've further learned that between chlorine and bromine, chlorine is producing an excess of energy, so it's very reactive and will get multiple products, whereas bromine is more selective in the product formation, and we can understand and predict which monobrominated product will be preferred based on classification of the CH bond. So if you like this screencast, please hit the like button. If you have a comment, please leave a comment below. And if you would like to see more new content from this channel, please subscribe. Thank you.